The content presented is offered through Statistica Hub. Your support sustains Statistica Hub's commitment to providing high-quality educational resources for free through its open course programs. Explore additional courses on the Statistica Hub platform at www.statisticahub.com.
Hello everybody, welcome to the lecture number 8 of Bayesian Inference. And as you can see on the screen, we will be discussing some problems corresponding to Bayesian Framework. And in the previous lecture, we have discussed some problems corresponding to this. But we will be raising our bar in this lecture. We will be discussing some more complicated problems, focusing mainly on the priors, that how to choose a prior. That's the main question that comes around, okay, when you are dealing with a problem if the prior is not given to you. So let's see it. So the question came sometimes that how would you choose a prior? How to choose a prior, that is how to choose a prior information. So there are so many things. The first thing is there is no true or correct prior. Okay, you cannot say this prior is correct. You are choosing a uniform distribution as your prior, you are choosing binomial as your prior, or maybe you are choosing beta distribution as your prior distribution. So you cannot prefer one prior. There is no, that's why we are saying there is no true or correct prior. In some cases there are like expert opinions or similar studies that has happened earlier in that field that you are studying. These studies identify the prior, and these priors are said to be the informative prior. When you are basically having some kind of information, whether it is an historical information or whether it is an expert opinions, you are having some information, right? In the second case, if you are not having any kind of information, okay, so basically if prior information is unavailable, okay, if prior information is unavailable, then in that case, then you will be choosing a non-informative prior, or you can say weakly informative prior. As you can see, when we are dealing with the Bayesian framework, we always say that f of theta given y is proportional to fp of y given theta into pi theta, right? Where this is the posterior, this is likelihood, and that is my prior. Okay, so when we are having a prior information, we can give more weightage, or we can use that information. Why waste that information, right? We will use that information. But if I don't have any prior information, then I cannot give more weightage to this pi theta value, right? Because at that time that will not give me the valid result for the posterior distribution. So at that time we will be choosing a prior which is weakly informative, which will not be affecting my posterior distribution that much. Okay, so prior information or prior distribution is it best viewed as, it is not beast, it is best. It is best viewed as an initial value to a statistical procedure. Okay, so what is the initial information you have about any experiment or about any question that you are doing? Okay, so, and if you will say that if the prior is irrelevant of like any expert can have different opinions, different experts have different opinions about something. So yes, you can choose different priors. You can calculate the same experiment, you can have the same experiment, you can deal with the same experiment with the help of different priors, and by picking the different priors you will be having some different results also. That is completely fine. Okay, so it depends on the prior that what you are choosing. Okay, so to understand it, let's take an example firstly. Yes, so for an example, consider that you are in a balloon shooting fair. Balloon shooting fair. Okay, so when in a balloon shooting fair, you have total tried 100 times. Okay, you have a gun, you have tried 100 times, and out of these 100 times you have hit it 60 times. Okay, 60 times you hit the balloon, you have tried 100 times. So let's say n is equal to 100, the total number of trials, and y is equals to 60, that is the number of balloons that you have hit. Okay, so in this model, when we are saying you have tried 100 times, you have hit it 60 times, it is very reasonable to consider a model for the number of hits that you have occurred. Y is the number of hits that have occurred. You can say that y is following some binomial distribution with the parameter n and theta, where n is the number of total tries and theta is the parameter. N is known, the only unknown factor is theta, which is parameter, and we know that theta is the true probability of successful shooting. Okay, probability of success. Now, as this is the probability of success, this parameter theta belongs to 0 to 1. Okay, now my prior information in this case would be, what would you think is the probability of success of hitting a target? So what is the probability of hitting a target? So that is your prior information. So what prior you should choose for theta? Theta is the prior here. Okay, so in most cases we can select a prior that puts on probability between 0 and 1, because my theta is having a range between 0 and 1. So I will think about some distribution which would be having a range between 0 and 1. Let's say I can consider a uniform distribution. I can consider any distribution which is ranging between 0 to 1, because my theta is bound between 0 to 1 as it's a probability of success, right? So let's say I don't have any information about what is the probability of success here. So in that case, by this point, we will be choosing a prior which is a non-informative prior. Okay, so if we have no relevant information, then we will be choosing a weakly informative or non-informative prior. Okay, and we will see that later, but yeah, there is one weakly informative prior which is a uniform distribution. So let's say that your theta is following uniform distribution from 0 to 1. Why 0 to 1? Because my theta is ranging from 0 to 1. Okay, so we have choose theta which is from 0 to 1. Now we are already saying that y given theta is following binomial n which is 100, that is n is known, and theta which is unknown. So this is following 100 comma theta. Now we want to know what is the posterior distribution for theta given y, and by the help of Bayesian framework we can say that this thing is proportional to f of y given theta into pi theta, right? That is proportional to f of y given theta is a binomial distribution, so it would be like, I know that y given theta's PDF is ncy theta raised to the power y 1 minus theta raised to the power n minus y. But ncy is a constant term. It will behave as a constant term, so it will go into the proportionality constant. So we will be considering the terms which are having a parameter. So that is theta raised to the power y 1 minus theta raised to the power n minus y, and pi theta, that will be 1. Okay, so we are having the posterior distribution like this. So if I rewrite this distribution, that is basically y plus 1 minus 1 and 1 minus theta n minus y plus 1 minus 1. Now if you recall it, then this is the beta distribution. your P of theta given y is following beta distribution with the parameter y plus 1 comma n minus y plus 1. What is a beta distribution? If you don't remember, beta distribution is the one whose range is from 0 to 1 when let me write it again. X is following beta distribution with the parameter a comma b, then the PDF corresponding to it is x is lying between 0 to 1, then this is 1 upon beta a comma b x raised to the power a minus 1 and 1 minus x raised to the power b minus 1. Okay, so that's why with the help of this distribution we can say that our posterior distribution is following the beta on the parameter y plus 1 and n minus y plus 1. Now if you focus on the graph corresponding to this non-informative prior that we have considered, let's just take a simple graph. This is a theta and this is density. Okay, let's take the theta values as 0, 0.0, 0.2, 0.4, 0.6 till 1. Okay, continuing till 1, and the posterior, the density like 0, 2, 2, 4, 6, 8, like this. Now if I'll talk about the uniform distribution, the prior is basically theta. So f of theta is equal to 1. This is my prior. So if I'll draw it, it's just a straight line, right? Like this. This is my 1. So it will be drawn like this. This is my prior. Okay. And if I'll draw a posterior, that is beta distribution. Now what is the, for y is equals to 60. For y is equals to, y is hitting 60. So what is expectation of theta given y here? What is the mean of beta distribution? That is a upon a plus b. So that will be 61 upon 61 plus, okay, that will cancel out, so I will just write it like this. So that will be here y plus 1 upon y plus 1 plus n minus y plus 1. That is y and y would cancel out, and we will be having 61 upon n plus 2, right? That is 102, and that is approximately 0.5 approx, or maybe lesser than 0.5. Okay, so it would lie, the mean, the peak of this distribution would be, let's say, somewhere here. Okay, for this density. So the posterior is, let's say, I don't have the accurate curve, but it would be somewhere like this, like this. Okay, so that is the curve for the beta for the posterior, and that will be the curve for the prior. Okay, now as you can see, this prior distribution is non-informative, as it does not have any parameter, right? The distribution does not having any parameter, so the posterior corresponding to it does not have any prior parameter in the formula corresponding to it. Okay, now let's say if you have any information, okay, if you have any information, because this uniform distribution is representing the prior ignorance. Okay, so if we have any information, then what we can say, we can consider that as my theta is ranging from 0 to 1, I can choose another prior for the theta, which is theta is belonging to the beta on the parameter a and b, because beta distribution ranges from 0 to 1, right? Okay, at that time, what will be the posterior? P of theta given y is proportional to f of y given theta and pi theta. Let's see, that will be theta raised to the power y 1 minus theta raised to the power n minus y, and this proportionality would be theta raised to the power a minus 1 and 1 minus theta raised to the power b minus 1, and that is proportional to, let's just sum it up, y plus a minus 1 and 1 minus theta n minus y plus b minus 1. Okay, now this by using the same distribution here, this is following P of theta given y is following beta distribution on the parameter y plus a and n minus y plus b. Now, as you can see here, you are having a prior which is having some parameter a and b. So it would depend on the values of a and b. In the previous case, we are having a prior which is a constant, so it would not affect the posterior. But if I change the prior, if I change the value of the theta, but here it would definitely affect it if I change the value of a and b. Now, if you look at the posterior parameters, it is depending on the parameters of the prior. So here I am having a certain kind of prior which will definitely affect the posterior. Okay, and the distribution that you just have studied, which is a very important distribution, that is one of the prior that you will see later, that if you are having f of y given theta which is following binomial n comma theta, theta which is following beta a comma b, and probability of theta given y, at that time the posterior is following beta y plus a comma n minus y plus b. This is one certain kind of distribution, and that is set to prior, that is beta binomial. Okay, beta binomial prior. We will see that also when we will see all types of prior: conjugate, informative, non-informative, all those things. Okay. Yep. And now let's consider some next problem corresponding to it. Let's discuss more. So let's consider firstly a simple problem. Let's say that I have collected some problems. Okay, so we will be discussing them one by one. That expert knowledge dictates that a parameter must be positive and its prior distribution, just give me a second, and its prior distribution should have mean and variance 2. Now they are asking, is it possible to choose an exponential distribution as a prior choice here? Okay, that's the question. Now let's see it. So firstly, yeah, they are asking that expert knowledge dictates that a parameter should be positive. That means whatever your parameter, let's say theta is the parameter, that is positive, greater than 0, and its prior distribution must have mean and variance 2. That means expectation of theta and variance of theta has to be equal to 2. Is it possible to choose an exponential distribution as a prior? Right. So they are asking, is it possible that theta is following exponential distribution? Let's see that. If theta is following an exponential distribution, then the mean and variance has to be 2. Right. So let's say theta is following exponential with the parameter lambda, and we know that the expectation of theta is 1 by lambda. Okay, and the variance of theta is 1 by lambda square. Okay, now expectation of theta is equal to 2, that is equal to 1 by lambda. By comparing, I got the value of lambda, that is coming out to be 1 by 2. Okay, now if I put this value in the place of variance, we will be getting 4, and here it is saying that the variance has to be 2. So that is not equal to 2. So you can say that exponential prior is not possible. Because if there is an exponential prior, then the variance has to be 2. Then the variance has to be 4. Okay. Yes. Now let's discuss one more. Next problem. That is, your daily commute is distributed uniformly between 15 and 20 minutes. If there no convention downtown. However, conventions are scheduled for roughly 1 in 4 days, and your commute time is distributed uniformly from 15 to 30 minutes. If there is a convention. Let Y be your commute item this morning. Then what's the probability that there was a convention downtown given y is equal to 18? Okay, firstly let's see the information what is given. That they are saying your daily commute is distributed uniformly between 15 and 20 minutes. Okay, our daily commute is distributed between 15 and 20 minutes. Let's highlight that this information. And it is distributed between 15 and 20 minutes when if there is no convention downtown. Okay. However, conventions are scheduled for roughly 1 in 4 days. These are the schedule for the conventions, and your commute time is distributed uniformly for 15 to 30 minutes if there is a convention. Okay. Now, why be your commute item this morning? Okay, why is the commute item this morning? Then they are asking what's the probability that there was a convention downtown given y is equal to 18. Let's say that theta is the variable which is convention downtown or not having a convention downtown. Okay, so we are saying theta is equal to, theta is taking the two values 0 and 1. 0 when it is denoting that there is no convention, and 1 when it is saying there is a convention. Okay, now it is clearly said that conventions are scheduled for roughly 1 in 4 days. That means probability that conventions are scheduled, there will be a convention, is 1 by 4. So by the help of complement, we can say that probability that there will be no convention is 1 minus 1 by 4, that is 3 by 4. Okay. Now let's see the next information. Your daily commute, y is your commute, y be your commute. Okay, y is commute. Then they are saying your daily commute is distributed uniformly between 15 and 20 minutes if there is no convention downtown. So y given theta following uniform 15,20 when there is no convention downtown. That means when theta is taking the value 0, right? Second, it is distributed uniformly from 15 to 30 minutes if there is a convention. That means if y given theta is equal to 1, that means if there is a convention, then it is following uniform with 15,30. Now we have asked that what's the probability that there was a convention downtown given y is equal to 18. That means we need to find anything, let's say P of convention downtown. There was a convention downtown, that means probability theta equal to 1 given y is equal to 18. Okay, if we'll let's expand it, that will be f of y is equal to 18 given theta is equal to 1, probability theta is equal to 1 upon f of y is equal to 18, right? And that is f of y is equal to 18 given theta is equal to 1. What would be that? That will be y is equal to 18 given theta is equal to 1. Just this. So what will be the PDF of this one? Y given 8 theta is equal to 1. That is 1 upon 15. 1 upon 30 minus 15. Right? That is 1 upon 15. Okay. So this value is 1 upon 15. Probability of theta is equal to 1 is 1 by 4. And probability f of y is equal to 18. Okay, that is f of y is equal to 18 is basically the rule of total probability that we have studied. That is f of y given theta is equal to 1, probability of theta is equal to 1, plus f of y given theta is equal to 0, probability of theta is equal to 0. Okay, so what is f of y given theta? That is 1 upon 20 minus 15, and that is going to be 1 by 5. Okay, so if I'll just put on the values, that will be 1 by 15 into 1 by 4 plus 1 by 5 into 3 by 4. If there is a mistake, let me know. Okay, and so this thing would be equal to 15 4. So that is 1 by 60, 1 by 60, 3 by 20. Okay, you can solve this. It's just a simple computation. That will be, let me do it, 1 by 60, 60 and 2 3s are 6, so 3 3s are 9, 10, and that will be, you will be having 1 by 10.1. Okay, so that's the 0.1 probability. Now in the same problem they can frame many questions. They can ask you that what's the probability that theta is equal to 1. Let's say they are asking what's the probability that theta is equal to 1 given y is equal to 28, right? Now in that case, if you will open it again by the same scenario, like f of y is equal to 28 given theta is equal to 1, probability of theta is equal to 1 upon f of y is equal to 28 given theta is equal to 1, probability of theta is equal to 1 plus f of y is equal to 28 given theta is equal to 0, probability of theta is equal to 0. Okay, and that will be equal to, now look for this case, by for theta is equal to 1, uniform 15 to 30, so 28 would lie in that, y is equal to 28, so 28 would lie in that range. So you can say 1 by 15 into 1 by 4. Similarly 1 by 15 into 1 by 4 in the denominator, and this case y is equal to 28. Now let's look at the range of y. Y is lying between 15 to the 20. 28 is not lying in this range. We know that the uniform range is 15 to 20 in this case, and 20 is not lying in this range, so the probability corresponding to it would be 0. So here, by cancelling out the terms, you will be getting the probability that will be equals to 1, because the reason behind that is convention is happening certainly as y is greater than 20. So after y greater than 20, it will be happening. Okay, you don't It will be a certain event after y greater than 20. Okay, we don't need to check it after that. Okay. Yes, let's now discuss the next problem, which is, I've a little messed it up, the slides, but yeah, as I'm speaking, so you can prepare your own notes. Yes, let's discuss the next question, which is saying that let x1 is following Bernoulli distribution with the parameter theta, where theta be the x1 be the indicator that a tree species occupies a forest. X1 is an indicator for this, that a tree species is occupying a forest. Theta is prior occupying probability. Okay, prior occupying probability. What is the probability that it is occupying a forest? Now, a researcher collects a sample of n trees from forest and x2 belong to species of interest. Okay, the model for data is x2 given x1 is following binomial. Let me write the parameters here, n comma lambda x1, where lambda is probability of detecting the species given it is present. We need to find out, let's do the first one, that is probability that x1 is equal to x2 is equal to 0. Okay, so firstly let's write down the information what has been given, that we are having a random variable x, which is actually an indicator variable that a species is occupying a forest. So x1 is following Bernoulli on the parameter theta, and theta is the probability that it is actually occupying a forest. And there is a difference, x1 is the indicator variable and theta is the probability of occupying a forest. A researcher collects a sample of n trees from forest and x2 are those which are belonging to that particular kind of species that he is interested in. And then he form a model that x2 given x1 is following binomial distribution on the parameter n comma lambda x1, where lambda is the probability of detecting the species given it is present. Okay, that you are actually detecting that it is present in it. Okay, so we have asked what is the probability that x1 is equal to x2 is equals to 0. Now, if x1 is equal to 0, that means x2 given x1, where x given x1 is equal to 0, that would be following binomial n comma 0, which means x2 would also be equal to 0 with probability 1, right? Because in that case, when we are saying x1 is equal to 0, then the probability of detecting this thing, probability of x2, probability of success of x2 would be 0, right? So this would happen, this is happening because if the species is not occupying the forest, x1 is equal to 0 means that if the species is not occupying the forest, then there is no chance, the probability is 0, that means there is no chance that the sample would contain any sample of that species, right? Because the forest is not having that particular kind of species, then it is not possible that if I draw a sample from that forest, I'll be getting some kind of species. That's why we are saying that x1 is actually, when we are saying x1 is equal to 1, that is x1 is equal to 1, that means species is present with the probability theta, right? Probability that the species is present is with the probability theta, okay? And x1 is equal to 0, that the species is not present, okay? Let me write it. Species is present and it is species is not present in the forest, okay? So if the species is not present, x1 is equal to 0, then if I'll take out the sample, it will be not having any species. So that's why we are saying that probability x1 is equal to x2 is equal to 0 is that basically means probability x1 is equal to 0, probability x2 is equal to 0 given x1 equal to 0, that will be equal to probability of x1 is equal to 0. We are saying here that probability that a forest is having a species is theta. That means probability x1 is equal to 1 is theta. So from here probability x1 is equal to 0. It is not having any species, 1 minus theta. So that is 1 minus theta. And we have just seen that probability x2 is equal to 0 when x1 is equal to 0 is going to be 1, right? Because my population is not having any species, then why? Then my sample would be not having any species, and I am sure about that. Okay, that's why the probability is 1. So 1 minus theta. Now in the same question, they can ask, let's see the B part. They can ask, what will be the probability of x1 is equal to 0 given x2 is equal to 0, right? That is easy. That you can find out just by the expansion of the, you can say the simple Bayes rule, and that will be probability that x2 is equal to 0 given x1 is equal to 0, probability x1 equal to 0 upon same thing, probability x2 is equal to 0 given x1 is equal to 0, probability x1 equal to 0 plus probability x2 is equal to 0 given x1 equal to 1, probability x1 equal to 1. Now just put down the probability. This is 1. Probability of x1 equal to 0 is 1 minus theta. This is 1 minus theta plus this is probability of x2 is equal to 0 given x1 is equal to 1. That is theta, right? So that will be probability of x1 is equal to 1, that is theta, and probability of x2 is equal to 0 given x1 is equal to 1. What will be that? x2 is equal to 0 given x1 is equal to 0. Sorry, given x1 equal to 1. Now to calculate this, you have the distribution that x2 given x1 is following binomial n comma lambda x1. So when x1 is taking the value 1, x2 is taking the value 0, your this thing would be 1 minus lambda raised to the power n, right? Okay, so that is 1 minus lambda raised to the power n. Okay, so by summing it up, we will be having 1 minus theta upon 1 minus theta plus theta 1 minus lambda raised to the power n. Okay, any doubt here? If you have any doubt here, this is just the binomial expansion, that NCX, like if you are having binomial with the parameter n and p, then it is NCX p raised to the power x 1 minus p raised to the power n minus x. I have just expanded it in the terms of when x2 is taking the value 0 and x1 is taking the value 1. In that case, it will be binomial n comma lambda, because x1 is taking the value 1. Okay, so binomial n comma lambda, and that will be, if I'll expand it in this term, that will be ncx2, which is 0. Okay, p raised to the power x2. Okay, that is lambda raised to the power x2, which is 0, and 1 minus lambda raised to the power n minus x2, which is 0. That is coming out to be 1 minus lambda raised to the power n. That's why I have substituted it here. It's just the binomial expansion. Okay, so that's the probability now. Okay, now let's see the C part. One more part in this question, and that is the interesting part, which is that if theta is equal to 0.5, lambda is equal to 0.1, and x2 is equal to 0, then how large must n be before we can conclude with 95% confidence that the species does not occupy the forest. That means when I've taken out the sample, x1 is whether the forest is having that particular kind of species or not. Okay, and x2 is when I have taken the sample from the forest, then whether I'm getting any sample of that species or not. Okay, so if I am not getting any sample of that species, then what sample size should I have so that I can say with a 95% confidence that the forest is not having that particular kind of species? Okay, so we are asking probability x1 is equal to 0. That means what is the probability that we can say forest is not having any species, given that we have collected the sample and we did not get any species in that sample. Okay, so that is equal to, we have just calculated it, that is coming out to be the same. I'll just put it here. Okay, we have already calculated it. That is 1 minus theta upon 1 minus theta upon 1 minus theta plus 1 minus theta plus theta 1 minus lambda raised to the power n. And we are saying we with 95% confidence that if my probability of this thing is greater than 0.95, then we can say that it will be, the forest will not be having any species. So we just need to substitute the value and calculate this equation for the value of n, right? So your theta is 0.5, that is 1 minus 0.5 upon 1 minus 0.5 plus 0.5, 1 minus lambda is 0.1 raised to the power n. We need to find out n from here to get the value of the sample size. That is 0.5 upon 0.5 plus 0.5, 1 minus 0.1, that is 0.9 raised to the power n greater than equal to 0.95. I can take out 0.5 common from the numerator and the denominator, and we will be having 1 upon 1 plus 0.9 raised to the power n greater than equal to 0.95. Okay, that is 1 upon 0.95 greater than equal to 1 minus 0.9 raised to the power n, and then we can do 0.9 raised to the power n. Sorry, it is 1 plus, okay, is lesser than equal to 1 upon 0.95 minus 1. and this thing is going to be 0.95, and 1 minus 0.95 is 0.05, and that is 1 upon 1 upon 19. Okay, now so we are having 0.9 raised to the power n lesser than equal to 1 upon 19. Taking log on the both side, it will be n log 0.9 lesser than equal to log 1 upon 19, log 1 upon 19, and this thing I can write as log 1 minus log 19 by the property of log m upon n is log m minus log n, and we know that log 1 is 0, so we will be having minus log 19. Okay, now that thing would be, you can calculate the value of log 0.9, log 0.9, log 0.9, that will be minus 0.046 lesser than equal to minus log 19, log 19, that is 1.2788. Okay, now multiplying minus on the both direction, the inequality would change, so that is n is greater than equal to 1.2788 divided by 0.046. Divide this result, and whatever you will be getting, that is the number of sample size that you are going to require for this statement to be said that there is no species of that particular type in that forest, given that there is no sample of that species. Okay, so yeah, these are some problems that we have discussed in this lecture, and in the upcoming lecture we will be discussing about priors. Okay, there are certain types of priors like conjugate prior, informative, non-informative prior, okay, uniform prior, all these kinds of things. Okay, so that we will see in the next lecture. We have seen one prior already, that is conjugate prior, so we will be deriving some all these priors like beta binomial and whatever the conjugate priors, we will see that. Okay, so yeah, that's the wrap of this lecture, and we will meet in the next lecture then. Okay, thank you, bye.